In this example, we're looking at a mechanism which is made up of three links, OA and AB and BD. OA is pinned to ground at O, BD is pinned to ground at D, and then those two links are coupled through link AB. What we know is that link OA is moving with a constant rate of 0.5 radians per second. And what we want to do is use that to figure out the angular velocity and angular acceleration of the other two links. Okay, so let's begin with our velocity analysis. Well, the geometry of this problem makes it relatively easy to get the velocity answers. Let me explain. We've got link OA pinned to ground at O. It's rotating with some speed of omega OA. So we can easily find the velocity of A. It's just L times omega naught. We construct a perpendicular to that. We look over at end B. Well, B is connected to BD. It's rotating about D. So its velocity is somewhere along this line here, because that velocity has to be perpendicular to the bar. We construct a perpendicular to that, and we see that based on instant center stuff is that the instant center of AB is at infinity. In other words, those two lines cross only at infinity. So what does that mean? Well, that means that omega AB is a zero. At that instant, it's in pure translation. So from this, we can see that VA, which is equal to L omega OA, must be the same thing as the velocity B. Because the body in translation, all points have the same velocity. And then since B is on BD, we can say that VB is equal to 2L times omega BD. So from this, we have that omega BD is equal to 1 over 2L times VB. VB is equal to VA, and VA is equal to L omega naught. So from this, we see that omega BD is omega OA divided by 2. And it's in the counterclockwise sense, because VB would be like that. So right away, with just a couple lines of analysis, we have the answer for velocities. Acceleration, not quite as easy. What we'll do, though, is use the usual procedure of doing it link by link and saying that the acceleration of A is equal to the acceleration of O plus alpha OA cross with the vector which goes from O to A minus omega OA squared, we know that, times the vector which goes from O to A. O is a pin. Omega OA is known to be a constant. So the acceleration of A is simply minus omega OA squared. The vector from O to A is an LJ. So that's link AB. So now let's go over to link BD. So acceleration B is equal to acceleration D plus alpha BD. We don't know that. Cross with the vector which goes from D to B minus omega BD, we just found that, squared, our B with respect to D. D is pinned to ground, so we have that. Alpha BD, we'll write that as an unknown in K. The vector going from D to B, that's 2LJ minus omega BD squared 2LJ. So what we have for AB is equal to minus 2L alpha BDI minus 2L omega BD squared in the J. Okay, so we've looked at links AO and BD, we now look at link AB and say the acceleration of B is equal to the acceleration of A plus alpha AB crossed with the vector which goes from A to B minus omega AB squared RB with respect to A. Okay, let me write this down. A sub A, and this is alpha AB, unknown, so we'll leave that just as K. Cross with the vector from A to B, that's 2Li plus Lj. Like that. And then what I will do is take the expression for A sub A and put that on the right side. On the left side, I'll put A sub B. Well, let me not do that. Let me write this down first. A sub A, and then I have minus L alpha AB I plus 2L alpha AB J minus 2L alpha AB squared minus L alpha AB squared J. There should be an I here. Okay, now what I will do is say that we're going to put the above expression for A sub A in there, put the expression for AB on this side here, and then I will equate components. The I components from B, AB is going to be equal to minus 2L alpha BD. From A sub A, there is none. And then from the other terms, there's going to be minus L alpha AB like that. There will be a minus 2L omega AB squared like that from the omega squared R term. Looks like I'm missing a minus or an equal sign somewhere here. Let me try that again. From the left-hand side, we have minus 2L alpha BD. Right-hand side, there's nothing from A, so the equal sign would have gone there, and therefore we have a minus L alpha AB. We have a minus 2L omega AB squared here. There we go. The J components from A sub B is going to be minus 2L omega BD squared. That's coming from A sub B. A sub A has minus L omega OA squared. And then we have a 2L alpha AB and a minus L omega AB squared. So we have two equations, and the two unknowns that we're trying to find here are alpha BD and alpha AB. So my suggestion would be to take this equation and solve for alpha AB. That gives us that. Once we have alpha AB, the first equation then can be used to solve for alpha BD. So none of the simplicity of the velocity equation carried through here on the acceleration. It ended up being a full-blown three-link mechanism thing where we have an acceleration equation for each link, and in the end we have two equations that we solve for two unknowns of alpha BD and alpha AB. But if we do go back up to the velocity stuff here, I think always take advantage of this whenever you can. whenever you can observe something like this, where the velocities perpendicular to the velocities of A and B in this case intersect at infinity, that means that the instant center is an infinite distance away, and therefore the omega for that bar must be a zero. And that really simplified things. Once we had that, we knew that AB was in translation, A and B had the same velocity, and we were able to easily get the angular speed of BD. I guess maybe down here something should have simplified out. The omega AB, that would have been a zero in that. So it's not quite as bad as it looks once we take advantage of that.